So we started our discussion on multi-component reactions, and there we first covered the combustion process, combustion of hydrogen and oxygen to produce water. And today we will be discussing about another type of multi-component reaction, which is the atmospheric chemistry. Now, under atmospheric chemistry, again, we will be talking only one particular problem, that is basically formation and destruction of ozone. And there are many atmospheric processes or atmospheric, we are talking about atmospheric chemistry, which is again photochemistry, because it's all initiated by the ultraviolet radiation that reaches the atmosphere, upper atmosphere. Now, ozone formation and destruction is very crucial for our survival, because you know that ozone absorbs the harmful ultraviolet light, and for which we survive. Because if it reaches on Earth, we can have many deleterious effects on our body, which are extremely deleterious for us. For example, it can cause damage of DNA, and that can cause light-induced cancer. So mostly the skin cancer. Now, the question is, what are the formation and destruction processes of ozone in the atmosphere? Now, ozone is encountered in every layer of atmosphere. You also encounter ozone in this region of the atmosphere which we live in, the troposphere. But then you see a steady decrease of ozone. And usually, if I draw the curve qualitatively, if I plot, say, the concentration of ozone and versus the height from the sea level or the altitude, so then we will see it varies very interestingly, like it goes like this. And what I would like to point out here is that at zero altitude, or basically on Earth's surface, we have some ozone, and then it decreases, and then again it keeps on increases and reaches a maxima. And this region, all of you know, at some altitude, let's say which occurs around 20 to 50 kilometer region. So this is basically the height for this layer, which is known as ozonospheres. You have learned this term in your geography course. Now, there you have a very high concentration of ozone. Now, the interesting thing is the abundant species in atmosphere are oxygen and nitrogen. And oxygen is the major source for ozone. As well as ozone also produces oxygen, but the total amount of ozone is very less. And if you think that if I increase the altitude, and the air pressure of course reduces, and if you had all the ozone, and if you put it in all the ozone which is present on Earth atmosphere, then if you compress it to 1 atmosphere pressure, you will find that all the ozone will basically cover only few millimeters, 2 or 3 millimeter height. So which means actually ozone, the volume of ozone, or the amount of ozone is very less, but that is extremely important. So compared to oxygen and nitrogen, ozone is actually a trace element, trace molecule in atmosphere, and but still its existence is very important for our survival. Now, there are many models for formation and destruction of ozone. So one of the very well accepted mechanism, it's well accepted in the sense that it's one of the preliminary well accepted mechanism. There are also other mechanisms that we will not discuss about all those things, but we will discuss the most standard mechanism, which is known as the Chapman mechanism, which was provided by suggested by Chapman. And then the Chapman mechanism says that the oxygen in our upper atmosphere, that actually absorbs light. So I write h nu as the energy of the photon that is being absorbed, and this h nu, say we can write it as a photon. So we could also write it as hc by lambda, the energy of a photon. Remember that energy of a photon is nothing but h nu, which we could write it as hc by lambda, where c is the speed of light in vacuum, or hc nu bar, where nu bar is the wave number. So this lambda is less than 242 nanometer, and below 242 nanometer photons are absorbed by molecular oxygen in the upper atmosphere, and that actually produces the oxygen radicals. And again, this is a radical chemistry, just like we discussed about radical chemistry in the earlier course, bromine and hydrogen reaction to form HBr. And also in this course, in the previous section, we talked about hydrogen radical and oxygen radical, and there we emphasize that the hydrogen radical is the predominant species which actually takes the reaction forward, not the oxygen radical, because that is O bond energy is much higher. Now this this oxygen radical in the next step actually reacts with another oxygen molecule and to form ozone. But now you see that if I have one oxygen radical and one oxygen molecule, is just an ozone is just like an adduct, like it's forming a bond. But then if there is a bond formation, some energy has to be released and somebody has to take up that energy. So we in the same token, like we discussed earlier, that we write something like M, where M is the third body that actually absorbs the energy. And that M is usually the oxygen present in the atmosphere or the nitrogen, because these are the predominant species. Now as you can see, the overall reaction, if we want to balance it stoichiometrically, so I have to multiply it by 2, because I have 2 oxygen atoms which was generated in the first step, and then I'll have an overall mechanism for formation of ozone, and that is O2 in the presence of light, H nu, and that actually forms 2 O3, and here I have 2 O2, here I have O2, so I'll have 3 O2. So this is the overall balanced chemical reaction. Now just like ozone is formed in the presence of less than 242 nanometer light, the ozone also absorbs light, and then it can actually degrade photochemically to form oxygen and molecular oxygen and oxygen radical. Now this is I do not have the wavelength here, but this is usually the wavelengths which are above this 240 nanometer. It is a longer UV wavelength, and where actually ozone absorbs, it will be around it's more than 242 nanometer wavelength. So this is also UV photon, but that's a longer wavelength UV photon. Now this mechanism, the destruction mechanism I have shown here. So this is not a very predominant mechanism. The reason is moment you have the radical can also collide with O2 and give you back the ozone molecule. Now the predominant destruction mechanism is another way. So this radical can also react with molecular the ozone which is present. This is not a photochemical reaction. This is just a collision reaction, and then you can actually form 2O2. So now actually I can write the rate constant for all these processes. Now let us just write the rate constant for this as J1. Now I'm not using the K notation here because it's a photochemical reaction, and secondly I'll use the K notation for the collision induced reaction. Like this is the second reaction, so if I call this as the first reaction, this is the second reaction, and this was the third reaction, which is also a photochemical reaction. I'll write it as a J3, the rate constant, and the fourth one was basically again collision induced reaction, so I'll write the rate constant as K4. Now as before, we are assuming that already we said that O3 concentration, ozone concentration is much less, so we can assume that the oxygen radical concentration that is forming the ozone is also less, and they are in a dynamic equilibrium, in the sense that this oxygen concentration as well as the ozone concentration in the upper atmosphere will be independent of time, meaning the ozone oxygen radical concentration as well as the ozone concentration are always in a steady state. So if we assume those things, our calculation will be easier. And then so first of all we have to find out what are the rates of oxygen radical formation from this above equation, and that will make it subsequently to be 0. So that rate, let us not put the 0 right now, we'll just see it afterwards. So that rate, if you follow the first equation, you see that 2 oxygen molecules are formed. So for this rate, again, if I write the rate constant, the stoichiometry will be here 2 of oxygen. So I have to write the rate of formation of O as half dO dt. So that half, due to that half, I have to multiply it by 2. So I'll have 2 J1 into O2. Now remember that when we were discussing the hydrogen oxygen reaction, there we took a rate constant which is omega 0, which is here. So there we have a slightly different notation, because we said that this omega 0 is the rate, it's not exactly rate constant, it is the overall rate. And that's why if you remember that dH dt we are taking as omega 0, not as twice omega 0 into H2. That omega 0 itself was a rate, it was not a rate constant. And here we are talking about a rate constant, which is the J. So we'll use it as we use the other rate constant in chemical kinetics. So it will be 2 times J1 into oxygen molecule concentration. And then we have the second reaction, as you can see here. In the second reaction, actually oxygen radical that gets decomposed. So or we can actually first write the J3 one, where actually it is being formed. If you look at the J3, it will be nothing but J3 into O3. Now let us consider the destruction paths, which is step 2 and step 4. Now step 2, it is basically O and O2. So we'll have concentration of ozone times K2 into concentration of oxygen times concentration of the third body into, I'll have the concentration of oxygen radical, but that I'll take common with the J4. That's what I'm just writing it outside. And plus for the fourth step, I'll have it will also be minus, so that's why I'm taking it within the bracket, and I'll have K4 into O3 into O, and that O I have taken common, and that I'll eventually make to be 0. So I can right away solve for O, but before under the steady state approximation, but before that let us also find out what is the O3 concentration, how it is changing with time. Now if you go up, O3 is appearing here in the equation 2, maybe we can use the same color here, and then O3 is appearing here also, and also equation 4. So let us just first write the formation of O3, O from O and O2. So this will be nothing but K2 times O2 times M and times O. Then O3 is being destructed in step 3 and 4. So we'll have minus J3 into O3, and it is K4 into O3 into O. So we can actually write it in that way, plus K4 into O into O3. That also will keep eventually to be 0. Now then if we apply the steady state condition from this first equation, what we get is oxygen atom concentration. Now this is very straightforward. As you can see, I'll have 2J1 into O2 plus J3 into O3 minus, not minus, divided by, because I'll just divide by the entire thing which is in the parenthesis. I'll have K3 into O3 into M plus K4 into O3. So that is the steady state concentration of oxygen radical in the upper atmosphere. And similarly, we can also figure out what is the steady state concentration of ozone in the upper atmosphere from this equation, and that will be nothing but K2, this is also very straightforward, O2 into M into O divided by, we'll have J3 plus K4 into O. So then what we have to do, you see here that we have written the oxygen radical steady state concentration in terms of O3, and similarly we have written the O3 concentration in terms of the oxygen radicals concentration. So basically these two equations and for two unknowns, and we have to solve it, and we can easily solve it. And if you solve it, then you can actually get O3 concentration. Basically what we are doing, we are putting the value of the oxygen radical concentration here in the in this second equation, and then you will have a quadratic equation, of course. And then if you solve it, I'm not showing you the solution because it is very straightforward. Wherever I have this O atom concentration, you have to write this entire term, and then basically I can show you one step, and then you can try solving it by yourself. So it will be K2 into O2 into M times O, and instead of O I am writing 2J1 O2 plus J3 into O3 divided by, I have K3 into O3 into M plus K4 into O3, and in the denominator we have J3 plus K4 into O, and again we'll substitute for oxygen atom concentration, 2J1 O2 plus J3 into O3 divided by K3 into O3 into M plus K4 into O3, and that now you can see that this part, this entire part, that I can multiply it by J3 and then eliminate that part from the numerator and the denominator, and then what we'll get is something like K2, I'll have O2 into M times, we'll have 2J1 O2 plus J3 into O3 divided by, we'll have J1 into the entire thing, J3 into the entire thing, J3 into K3 O3 M plus K4 O3 plus we'll have K4 into twice J1 O2 plus J3 into O3. So this entire equation you have to solve, and on left hand side also I have O3. This is steady state. All the O3 is actually O3 is steady state. So don't get confused that this O3 steady state is different than this O3. So this is just a notation because we have already approximated it to be 0, and that is the steady state condition for both ozone as well as the oxygen. And then as you can see, we will have a quadratic equation, and then if you solve the quadratic equation, so I have done a few steps and you can solve it, and then what you will get is the final answer for the O3 concentration. Let me use a different color for this. So the O3 concentration will be, in terms of oxygen concentration, the molecular oxygen concentration, O2 into J1 by 2J3 times we'll have 1 plus 4 J3 by J1 into K2 by K4 times M, and this entire thing square root, the square root is coming because it's a quadratic equation, minus 1. And now, so what you can see here, this is a rather very complicated complicated expression. Now we can actually estimate the magnitudes of O3, which is the ozone concentration, and O concentration. From we can how do you get it? You can actually get it from the data. Now how do you do this experiment? From upper atmosphere, you can do it in many different ways. For few atmospheric chemistry experiments, you want to simulate it in the lab if you know the concentration and many other things. But if you want to do real experimental data, so what you do is a balloon experiment. So basically you launch a balloon which will collect the composition of the gas from the upper atmosphere, and then you take it back, and then you basically look at the kinetics there. And for kinetic measurement, you mostly use the absorption based experiments. There are also mass spectrometric based experiments, so and then you combine all these data, and then you calculate what are the rate constants. But you can also get an idea from the J rate constant from measurement of photon flux in the upper atmosphere. So then for all these values, let's say at we are saying at 30 kilometer, I have some data here which are real data collected from experiments. So J1, now if you see what is J1, J1 is this step where actually oxygen gets dissociated into the radicals. So that first order rate constant is 10 to the power minus 12 second, which means actually per second there are 10 to the power 12 times this thing is happening. So this is pretty fast decomposition. And the J3 is 3 into 10 to the power minus 4 per second. The unit should be per second. What was J3? If you remember, J3 is this step where the ozone actually gets decomposed into O2 and O, and as I said that the O2 and O, because since O is very reactive, can again get back form your ozone molecule. So this rate is much smaller compared to your J1. And then we also have the thermal rate for decomposition of ozone. It's basically ozone and oxygen radical reaction to form two oxygen molecular oxygen species, and that rate, which is the K4, that is something about 10 to the power minus 15. Now it is a bimolecular reaction, if you remember. So it's an overall bimolecular reaction. This reaction, as you can see, so the rate constant will also be, cannot be per second because it's not a unimolecular decomposition. So it will be 10 to the power minus 15 centimeter cube per molecule. So we usually are not using the mole per liter unit. So here actually it's a molecule per cc unit, and it's a reciprocal of that concentration. and times second inverse. Because if you remember if we for any second order rate equation, so the rate constant is something like k into the concentration of the species. Let's say the species is A, another species is B, something like this. Now how do you write the rate? Rate is basically concentration, rate of change of concentration per second, and then I have K, and then I have concentration, and I have concentration here. So the unit of K will be basically concentration inverse, second inverse for a second order reaction. So this is exactly what we have done here. So just check the units. And then for the three body recombination, there are some tabulated function, in the sense that you can get it again from a huge after you collect huge data from your balloon experiment and many other experiments. And then there are some standard tabulated data. So for K2, now the K2 was basically three body rate constant, and that we will write the equation, we write the units correctly, but before that we are just writing the table. So it basically forms some very complicated power law with temperature, and at the temperature which is around say 30 kilometer altitude, that K2, if you calculate from all these parameters, you will get all the atmospheric parameters, you will get something 2 into 10 to the power minus 33 centimeter to the power 6 per molecule, and then second inverse. This should be per 2 molecule because I'm taking the square of that, that's why it is coming centimeter to the power 6. Now then if all the also what you need is the concentration profile of O2, because as you can see the O2 is here, and you need a concentration profile of O2 at 30 kilometer altitude, because as we said, the majority of the ozone actually stays between 20 to 50 kilometer altitude. And then you can actually calculate the O2, and this O2, again these are just data which I'm writing just to give you a feeling what will be the final result of these rates. And that O2 concentration is found to be 10 to the power approximately 10 to the power, this is also kind of, all are actually approximate, so we don't need to write it for oxygen molecule concentration explicitly. 10 to the power 17 molecules per centimeter cube, and then the total M, which is basically the as I said, that M is a third body, but the third body is the abundant species, and that abundant species are oxygen and nitrogen, and that if you calculate, it will be 5 into 10 to the power 17 molecule per centimeter cube. Now why 5? Because as you know that we have 80% nitrogen and 20% oxygen. So if oxygen is 10 to the power 17, so that forms actually 1/5 of that. So the total M of the third body will be 5 into 10 to the power 17, and then we can actually estimate this term, which is K2 into M divided by K1, and that will give you something like K2 into M divided by K1, that will be 0.6, and J3 by J1, that will be around 10 to the power 8, and which now can lead to a more simplified expression. So as I can see here, so I have K2 here, and I should have a K1 it's not K1, it should be K4, K2 by K4, and then after you use all these parameters, so that will give you the ozone concentration is approximately equal to the molecular oxygen concentration times J1 by J3 into K2 by K4. Now this into m to the power half, and then you can actually evaluate the O3 concentration for several species. I mean, like if you know the values of put the values of J1, J3 as well as K2 and K4, and also the estimated value of m, so that will give you something around 6 into 10 to the power 13 molecules per centimeter cube. So this is basically the final value for ozone, which is around 30 kilometer. Now here, as you can see, going from here to here, this expression, we made some approximations, because we said that what is the relative ratios of K2 by K4 into m, and what about the J1 and J3. So all these values we put, and that's why you are getting this particular equation that we have shown here. Now if you move on, so I'll just leave it as an exercise how you get this particular expression, which I am putting it in the box, from this expression, which we kind of showed. We did not show the derivation, we showed only a part, how to proceed, and then we said that you try to derive it. So you try this derivation, and once you get that expression, try to figure out how this relation is coming under these approximations, not approximation, under these experimental values, and then if you can use those experimental values to approximate means actually you can neglect some of the ratios of the rate constant or some concentration, and how we can get this approximated value of ozone at say an altitude of 30 kilometer at a particular temperature which corresponds to that particular altitude. Now what is interesting is that you see, in a similar way you could also calculate the oxygen radicals concentration, because remember that we wrote the oxygen radical also in terms of O3, and then we put that value in the equation of O3. So that you will get around after you put all these values, it will be something like 10 to the power 7.4. Now you have to be very careful, this is basically particles per cc, but I cannot write it as molecule per cc. It is basically those many atom per cc. So molecule per cc means it's molecules per cc. We could write it as atoms per cc. Now if we now rearrange these equations, which is the O3 expression, let us go back where we got this value. See the expression of say O3. Let me actually use a different color. So this expression, so I have K2 into O2 times M into O divided by J3 plus K4 into O. So that equation, if we rearrange a little bit, then we'll get K2 into O2 into M divided by K4. The K4 one we are just putting up, and in the denominator I have J3 divided by K4 into O plus 1. So that is very straightforward. We are just dividing the numerator and the denominator by K4. And then since we know that this thing J3, we already know that thing J3 divided by K4 into O, so that will be on the order of let's say it will be something like 10 to the power 4. How do you get it? You can easily get it from these values. You have the J3, you have K4, and you also calculated an approximate value for O, this one. And if you put back all these values, which is much larger than 1, so this is much larger than 1, so I can actually neglect the 1 value here, and then this expression, if I use this condition, this expression for O3 now becomes something like K2 into O2 into M divided by J3 into O. So we have J3 here, or we could write it as the ratio of O3 and O. So we have O3 here, and we have oxygen atom in the denominator, J3K4 into O. Let us actually have a quick look. So what we are writing here is J3 into O. So I have already ignored the 1 compared to that. So you can actually ignore that. Yes. Now you can actually, from this you can calculate the ratios of the ozone and the O radical, and this is very important. Now why it is important? It is important, suppose if I just take that particular ratio O3 and O, let me quickly also check the O3 value here before we discuss. It was K4 into O, as we can see here. So now let us go back and see what was the value of O3 which we got in terms of oxygen radical. We can actually rewrite this expression. So I'm talking about this particular expression, O3 steady state, which is K2O2 times M times O divided by J3 plus K4 into O. Let us just rewrite it here. So O3 concentration, which we got earlier, in terms of the O concentration or the oxygen radical concentration, is K2 times O times O2 times M divided by, we have J3 plus K4 into O. Now we can actually divide the numerator and the denominator by K4 into O, this term. So let us write it, what will be the final expression. So I'm just rearranging the terms again. So it will be K2, O will cancel, I'll have O2 into M divided by K4, and then I'll have J3 divided by K4 into O plus 1. So that is just a rearrangement. Now the thing is, this J3 into K4 into O, that value we can evaluate from all these parameters that we have written, like J3 here, we have K4 here, and we have also estimated the O here. So what we can write here, like J3 divided by K4 into O, and that will come around 10 to the power 4, which is much larger than 1. So this term is much larger than 1. So what we can say that this is approximately will be, if I just ignore the 1 and again multiply the numerator and the denominator by say K4 into O, finally what we will get is something like this. We'll get O3 divided by O will be equal to K2 times O2 times M divided by J3. Now this is a very important relationship, because this is an overall equation where we see the ratios of ozone molecule present in that higher altitude divided by the oxygen radical concentration. Now this concentration, as we can see that they are kind of the ratios of the odd oxygen species which is present in the upper atmosphere. Now this if we can actually the reactions that destroys either oxygen or O3, now that can result in a direct reduction of O3, and in the removal so that way we can actually see this particular ratio actually is very important to know about how much the destruction process or the formation process is happening, because if we have more ozone coming, then this ratio will be high. But if we have the oxygen radical species which are more, then I'll have the decomposition of ozone also will take place because of the fourth reaction K4, and we have already estimated or shown you some of the values of the rate constant, and that is a non-negligible value, the K4 values. So this ratio is very important, whether I am actually enriching ozone or I am actually decreasing the O radical concentration. And since more or less all these values K2, O2, Jm and J3 are kind of constant, then this is also a constant. So that's why the ratio of the ozone and oxygen radical, that always is kept at constant. And although we said that individually also they are constant, because all these things we derived, remember, using the steady state approximation for both oxygen radical, O radical, as well as the O3, the ozone. So individually they are constant as well as the ratio is constant, but this ratio actually fluctuates from one particular atmospheric region to the other atmospheric region. Now what I did not discuss in this particular formation or destruction of the ozone, there are also other atmospheric products, like say for example chlorine cycle, and then you have chlorine actually forms many oxide compounds which we call as ClOx, where X can be 1, 2, something like that. Similarly, I also have nitrogen oxide cycles which are called as NOx cycles. So these NOx cycles, clock cycles, as well as the HO cycle, which is Hox cycle, which as a part of it we also talked about, because we talked about OH radical chemistry a little bit when you talked about H2 and O2 reaction, but that's a combustion process, that is basically man-made process, but it can also happen atmospherically. And all this, the beauty of this and the complexity of all these processes is that they are kind of coupled, because you will have some common spaces. Now as I said, that ozone cycle you have the oxygen radical, that oxygen radical is not a part of ozone cycle, it also is a part of the clock cycle, it is also part of the other cycles. So the problem here is that all these cycles are not independent of each other. The way the Chapman model actually approximated it is not fully correct, because there is a very complex connection between this through this intermediate or the common species, common radical species, it can be molecular species, and for that all these cycles are interconnected, and that makes the atmospheric chemistry, the study of the atmospheric chemistry, which we have to study because of our own survival, and that makes the subject so interesting. Because you have so many parameters and so many coupled differential equations. So we'll not actually talk about the details. But the final thing is that this use of these chlorofluorocarbons, as you know that this kind of molecule CF3Cl, which is known as freon. So this was used for refrigeration as a coolant agent in refrigerator, and then people found that this CF3Cl gets into the atmosphere, and that forms this chlorine radical, and that actually is an important constituent of the clock cycle that actually produces the oxygen radical, this species, and that eventually can destroy the ozone, all these reactions which we have discussed. But again, we have not discussed the full photochemistry of ozone, and people found that these are very, very harmful, and that actually create ozone hole in and that leads to basically penetration of the harmful ultraviolet radiation through this ozone hole and to the Earth's surface, and that causes skin cancer, and that's why chlorofluorocarbons are banned to be used as a refrigerant coolant. And so three people actually brought enormous insight among many others into the mechanism of this formation and destruction of ozones, Mario Molina, Paul Crutzen, and Cheryl Rowland, and they were given the Chemistry Nobel Prize for their interesting work. So in the handout we will mention this particular work by Molina, Sherwood, and Rowland, which actually led to all these interesting discoveries and making a connection of the chlorofluorocarbon, how it influences or basically leads to the formation of the ozone hole, which is very dangerous for us. So we'll stop our discussion on the multi-component reaction here. So we talked about combustion chemistry, we talked about the ozone formation. So in the problem set, what we will be asking is that we will ask you to work out other problems like other cycles. For example, for combustion, there are also hydrocarbon combustion. We can actually give a problem on this hydrocarbon combustion, and for example, for atmospheric chemistry, we can actually give a problem on this Knox cycle or clock cycle and ask you to solve the differential equation. Again, these are all just simple mathematics, and you just have to choose, and we'll give you this information that which radical species you take to be under the steady state concentration, and you make that approximation, and then you just solve the differential equation, and then we'll also give you some values to make further approximation, and then at the end of the day you should be able to get a feeling. So what are the how this understanding of the mechanism can actually lead to an understanding of a very, very common phenomena, like as I said, that the formation of the ozone hole or something like that. So we'll stop our discussion here on the multi-component reaction. Thank you.